Good afternoon, everyone. In this presentation, I will show how medical-grade computed tomography, or CT, can be used to determine the depositional history of a sedimentary succession. Now, this work is a joint collaboration between the University of Ottawa and the Geological Survey of Canada. As for the geological context, this map shows the maximum extent of the Laurentide ice sheet during the late Quaternary. The Laurentide ice sheet was up to 2 to 3 kilometers thick in some parts of Canada, and upon melting produced a substantial volume of meltwater discharge. Sediment-laden meltwater discharge was dispersed into the isostatically depressed Champlain Sea Basin, and the City of Ottawa is the focus study area for today's presentation. Alright, so why study the Champlain Sea Basin? Well, the rationale for studying glacigenic sediments of the Champlain Sea Basin is driven by their great societal interest, which is due to their potential susceptibility to retrogressive landslides, and their integrity as a regionally extensive aquitard in the Ottawa and St. Lawrence River valleys. The study area is located in the metropolitan community of Orleans in East Ottawa, where 2 boreholes were drilled and continuously cored, VC2 in the west and BC16 in the east, and they're separated by a distance of about 3 kilometers. And so cores were carefully retrieved, packaged, and then transported to the INRS laboratory in Quebec City. The cores were scanned using medical-grade computed tomography, or CT. CT is a non-destructive high-resolution technique for analyzing sediment cores, and it provides a 3D visualization of sediment based on variations in material density and atomic number. In this study, CT scan images were viewed in the sagittal and coronal planes, which are oriented perpendicular to bedding, and the transverse plane oriented parallel to bedding. In the examination of the CT scan images, grayscale values are reflected as Hounsfield units, named after Sir Godfrey Hounsfield for his part in the invention of the CT scanner. Hounsfield units are reflected as gray tones and are based on the level of X-ray attenuation, where dense material has a greater X-ray beam absorption and these materials appear bright, whereas less dense material has less X-ray beam absorption and appear dark. In the study of sediments and sedimentary rocks, HU values vary primarily with properties that influence bulk density, namely grain size and porosity. And in the remainder of this presentation, clay-rich sediment will appear relatively dark in the CT scan images, whereas silt-rich sediment appears comparatively brighter. This is a simplified cross-section of the stratigraphic succession, and it shows the vertical and lateral distribution of sedimentary units that were identified in this study. Each of these units is mud-dominated. There's 5 mud-dominated units. So what we're going to do is we're going to begin at the base, that of Unit 1, the mud rhythmites, and we're going to work our way through towards the top of the succession by examining each of these units in detail and how exactly they transition from one unit to the next vertically within the succession. Now, beginning with Unit 1 at the base of the succession, Unit 1 directly overlies the glacial till in the easterly borehole, and it's comprised of these mud rhythmites. We have these planar bases, a basal silt-rich layer overlain by an upper clay-rich layer. Well, one thing that we can do with the CT scan data sets is that we can generate Hounsfield unit or HU profiles for each of the cores. And so the white dashed rectangular line indicates the area where the HU profile will be generated. And let's focus on the red box here. Let's magnify the red shaded box. So what it shows is a magnified view of the core. And again, we can see it consists of these relatively thin beds. The Hounsfield unit profile shown here. Low HU is towards the left of the profile and high HU is towards the right of the profile. And if we look at each of these beds individually, what your eyes can pick up is that from the base upwards into the bed, there's an increase in silt content. And then continuing upwards into the bed, the silt content decreases. And so the increase in silt that we see from the base upwards within a bed corresponds to an increase in HU. And similarly, as we move from that point within the bed upwards, that corresponds to a decrease in silt content. And we see this in all of the beds. Each of the beds is characterized by an upward increase in silt, followed by an upward decrease in silt. And similarly, an upward increase in HU, followed by an upward decrease in HU. And so the upward increase in HU is interpreted as the waxing phase or increase in glaciogenic meltwater discharge into the basin. The maximum HU corresponds to peak meltwater discharge conditions, and the decrease in HU we see is the waning period or the decrease in glaciogenic meltwater discharge into the basin. Okay, so this is the same CT scan image from the previous slide, and what it shows is the full core HU profile. And adjacent to the HU profile is an interpretive flow discharge curve. And so what these two curves show is that each of the beds is characterized by an upward increase in HU, which corresponds to a waxing or increasing period of meltwater discharge, followed by a subsequent decrease in HU, which corresponds to the waning or decreasing period in meltwater discharge. Now, we do occasionally get these intervals in which HU remained high for a period of time. This is interpreted as these steady periods of meltwater discharge. In other words, the maintenance of relatively high energy conditions for a period of time. Then you get a subsequent decrease in meltwater discharge conditions. Now, the beds within Unit 1, these mud rhythmites, they are consistently on average about 2 centimeters thick. And as we move up within Unit 1 towards the top, there is this transition into bioturbated mud within Unit 2, in which beds abruptly thicken. So we go from about 2 centimeters thick in Unit 1 to consistently 4 to 6 centimeters thick within Unit 2. You can see that there's this transitional unit in which the bioturbation starts to appear, and then the core remains consistently bioturbated within Unit 2. Now let's have a look at Unit 2. Okay, so Unit 2 consists of this bioturbated mud. It's extensively bioturbated throughout. Beds are on average about 4 to 6 centimeters thick. And what your eyes can pick out is that within the core there is this distinctive banding, this repetitious banding, where you go from light, dark, light, dark, light, dark, and so forth throughout the core. It's relatively difficult to pick out bed boundaries, but with the use of an HU profile, it makes it a lot more simpler. So again, each of the beds is characterized by an upward increase in HU to a maximum point, followed by a subsequent decrease in HU. And again, here is the associated interpretive flow discharge curve. And so the use of the HU profile allows the bed boundaries to be picked out with great accuracy. We can also view this bioturbated mud unit in transverse planes. And so this shows various morphologies of these burrow fills that are either filled with concretionary material or relatively coarse-grained detritus. And some of the bright features shown here are burrow fills that are filled with concretions. And as we move up towards the top of Unit 2, we transition abruptly from bioturbated mud into this banded mud. This feature here, this is an escape and or readjustment trace, which is filled in with concretionary material. Again, the transition where we go from bioturbated mud to banded mud happens abruptly. Unit 3 is banded mud. It's characterized by this distinctive, repetitious light, dark banding throughout the core. Now, without using HU profiles, just based on the CT scan image, it's relatively challenging to pick out bed boundaries. Where is the bed base? Where is the bed top? And if you were to give this core image to perhaps 10 different people, you would very likely perhaps get 10 different answers. But with the use of an HU profile, there's no guessing as to where bed boundaries are. All of the beds are characterized by this rhythmic upward increase in HU, followed by decrease in HU. And the same is seen from the lowermost part of the unit to the middle part of the unit. Again, all beds characterized by an upward increase in HU followed by a decrease in HU, or upward increase in silt content, and your eyes can pick that out in the core image, followed by upward decrease in silt content. And the same is seen at the top of the succession. Now, beds in Unit 3 are on average about 8 to 17 centimeters thick, which is considerably thicker from beds of Unit 2, which are consistently 4 to 6 centimeters thick. Now, the banded mud beds of Unit 3 abruptly transition into these thicker, diffusely stratified or structureless mud beds of Unit 4A that are characterized by the same consistent rhythmic pattern in HU, Beds are characterized by an upward increase in HU, followed by an upward decrease in HU. And these beds, these diffusely stratified or structuralist mud beds, are in turn interbedded with well-stratified mud. So here's an example of diffusely stratified or structuralist mud. We see this gradual increase in HU that corresponds to the onset of well-stratified mud. Then we see this gradual reduction in HU corresponding to a decrease in silt content towards the upper parts of the bed. So what we see when we move towards the upper parts of the succession is we get the onset of deformed mud intervals. And this deformed mud is sharply intercalated with beds of undeformed mud of Unit 4A, what we looked at on the previous slide, those diffusely stratified or structuralist mud that were intercalated with beds of well-stratified mud. Here's an example where we have deformed mud intercalated with undeformed mud, and then sharply intercalated with deformed mud. Some of the Shelby tube cores exhibit intense deformation and the entire core length is completely deformed. So based on the CT scan images and Hounsfield unit profiles, I'd like to propose a depositional model for the succession. Now, during the early stages of deglaciation, sediment-laden discharge associated with the meltwater season flowed along the lake floor, forming bottom-hugging hyperpycnal flows. And these flows sorted sediment along the bed and generated the well-developed parallel stratification in beds of Unit 1. Continued deglaciation of the Laurentide ice sheet resulted in an ingress of marine waters from the Atlantic Ocean and the formation of the Champlain Sea. Now the increase in fluid density in the basin caused inflowing glacigenic meltwater discharge to instead form buoyant hypopycnal plumes, with sediment settling from the base of these plumes towards the bed. The increase in bed thickness and rare bioturbation in Unit 3 suggests a marked increase in sedimentation that also initiated a slow-moving density current that formed the diffuse parallel stratification and textural banding that we see in strata of Unit 3. And then the abrupt increase in bed thickness that we see at the base of Unit 4A, well, this suggests another sudden increase in sediment discharge into the basin. Now, the abrupt onset of deformed intervals of Unit 4B that are intercalated with beds of Unit 4A, well, this suggests that sediment deposited along the bed was at times gravitationally unstable and mobilized downslope as mass failures, possibly facilitated by a steepened basin margin. So what I'd like to also stress is that in addition to the characteristic sedimentary structures and textures that we see in beds within each unit, they're also consistent in their thickness, and the bed thicknesses increase abruptly from one unit to the next. And this is interpreted to be due to temporal changes in the rate of sediment supply, salinity, and/or water depth in the basin. And what we also see is that the range of HU is quite similar between units. Unit 1 and part of Unit 4A, in which the beds are well stratified, exhibit a wide HU range, a difference between the maximum and minimum value. And this is interpreted to be due to the physical transport process. The wide HU spread is due to hyperpycnal flows that sorted and segregated particles along the bed, whereas the more narrow HU spread is interpreted as deposition from hypopycnal flows, where sediment was settling through the water column from suspension. And finally, just to emphasize, the unit transitions that we see are abrupt as we go from one unit to the next. And these abrupt transitions most probably reflect the abrupt systemic changes in deglacial dynamics and its control on sediment supply that often coincide with equally abrupt changes in salinity in the Champlain Sea basin. And currently we are working on a microtextural study to determine the grain composition, texture, and fabric of these fine-grained glacigenic sediments in order to assess the nature of pore fluid diffusion and the physical influence of these sediments on geotechnical properties. Thank you all very much for your time.